So in this second and final video for water and carbon, we're going to be focusing on the carbon and the carbon cycle. So to start then, what is the carbon cycle? Well, basically there's different forms of carbon. There's inorganic and then there's organic forms of carbon. Carbon atoms are found all over the planet. They're a building block for life. Origins of carbon is from the Earth's interior, from the mantle. When it was formed, it escapes at plate boundaries. Volcanoes is a part of the slow carbon cycle, which we'll come on to later on. So where is it stored? Well, slightly differently. We've got the cryosphere, biosphere, hydrosphere, atmosphere and lithosphere being the main stores. We do have the pedosphere as a substore, which is the soil, basically. Now, for us here, 99.9% is in sedimentary rocks. Okay, that's the key one there. Not a huge amount of that is in fossil fuels, but that's the impact that we're having by moving the carbon from the fossil fuels into the atmosphere. So there's the numbers for you. These are summarised there as a percentage as well, so you can take that. So the carbon cycle then has got a series of inputs, flows, stores and outputs like any one of our systems. The carbon cycle is considered to be closed because it is doesn't escape from our planet, the global carbon cycle. When you're looking at smaller areas, obviously there might be an output from that area of the carbon cycle. So if you're talking about a specific sphere, then you'll have an input, they'd have some flows and then stores and then an output as it leaves that sphere and moves to another one. We've got components and controls. This will determine the volume and scale and the sort of processes of the components within that. And within that then, there are different processes and types of carbon cycles. So let's look at this bit first. The carbon cycle itself then is this movement of carbon around our planet. It is a closed system, inputs and outputs remain the same with them. And this is how they interconnect. Worth taking some time to sort of get your head around this, looking at this in a bit more detail. But how is carbon moved between our different spheres, and therefore it's a cascading system again. Now we can look at this carbon movement on a range of spatial scales. So we do have a temporal element to this, the fast carbon cycle and the slow carbon cycle, which we'll come on to in more detail later on. But basically, like, you know, burning something is a fast movement of carbon. That's a temporal scale, but the lithosphere, locking it away in rocks for millions of years, that's a slow temporal scale for that. And then our spatial scale. Now we've got these processes, respiration, photosynthesis, the main flows within that. Then you've got sequestration in the sort of the longer continental scale. But let's have a look at this in more detail. When we're talking about spatial scales, small scale is at the plant level, a single tree, for example. So, you know, the movement of carbon in through photosynthesis, respiration out, leaf litter, decomposition, and so on and so on. On a sphere, not a sphere, a sphere, like a samosphere or a halosphere, we're talking about how more carbon is trapped as the vegetations change, as the succession of vegetation occurs. So how it traps more carbon. And then on the continental scale, you've got the slow carbon cycle, locking it away, sequestrating it for millennia. And that is basically the full carbon cycle, that one, the continental scale. All of those interactions from the diagram before, wherever that was, this one here. Okay, so that's the continental scale, how it's locked away in rocks and then how volcanoes chuck it back into the atmosphere. So let's look at the key processes that are involved in the fast and the slow carbon cycle. Let's look at the fast carbon cycle first. They're actually part of the fast and the slow, but for the fast bit precisely, we've got these main ones here. photosynthesis, respiration, digestion, decomposition, combustion, and then ocean uptake and loss, diffusion, basically as part of that. So take your time, have a look through some of those, learn the equations. That is how you will get detailed responses for this. In addition to that then, we have the processes that are part of the slow carbon cycle. So slow carbon cycle will be all of that from before, but then it has these additional processes of weathering, methanogenesis, sequestration, and then we come on to the oceanic carbonic pump. So let's just run through these quickly. Chemical weathering, so obviously the lithosphere is where most of our carbon is locked away. Atmospheric carbon reacts to that. It can be dissolved by weak carbonic acids, and that can make calcium carbonate, which is in water. Now this diagram here shows that in more detail, so take some time to look through that. Then we've got methanogenesis. Now this is basically when methane is released, and it's the last stage of decay. It's part of our digestion system as well, but basically it's from any anaerobic environment. Bacteria will release methane as a result of that decaying decomposition process. Now then, moving ahead to sequestration, this is basically the locking away of carbon, okay? So we'll talk about this going into rocks. There are other things we'll come on to in mitigation later on. You can have biological sequestration, locking away in plants, for example, but this is referring to sedimentary rocks or fossil fuels, but basically down in the ground. And it explains how, once it's in the ocean, it makes bicarbonate ions and calcium carbonate, and that's then used by corals. It can also be absorbed into plankton. They die, they get squashed and turned into a sedimentary rock under the pressure, or perhaps a fossil fuel later on. They then, might get moved around by your plate tectonics, and eventually that carbon will be released back into the atmosphere through volcanoes. Now, two additional things for this then. We've got the ocean carbonic pump. The ocean contains 50 times more carbon than the atmosphere, and it does exchange large amounts with it every year. So, what is going on then? Why is this? It can hold so much because of two different pumps that we've got going on. So let's take some time to think through them. We've got the physical pump. Now this is literally to do with different densities of water. Cold polar ocean water can hold twice as much more as warm water. Ocean currents move these waters from the tropics to the poles, where they cool, take up more CO2, and then they are denser, so sink, taking the CO2 accumulated with them downwards. That then goes back along the ocean floor to the tropics, which is then brought to the surface, warms and releases some of that back into the atmosphere, and so on and so on. So you've got these ocean currents, this physical pump. And then you've got the biological pump, which is kind of what we just mentioned, where carbon is stored in plants and shells. That requires light, happens at the surface. And then as they die, they sink deeper. And so on and so on. Okay, so they're the two different ones. The physical pump and the biological pump is what you need to know. So those are our key processes driving the slow carbon cycle, and that's summarised there for you with volcanic activity, then releasing our rock carbon back into the atmosphere. Okay. So now we come on to natural variations, and then how humans affect this carbon cycle as well, before we come on to the carbon budget. Now, the carbon cycle will change over time. We've already mentioned this, okay? There's natural ways that it can happen, and there's ones where it can be a lot slower. Now, how does this happen naturally? Okay, combustion, wildfires. that transfers large quantities of carbon to the atmosphere. We have vegetation changes over time. Glaciations might have an impact on vegetation type as well. So we've got, huge variations in this that can have an impact. I mentioned before with water about pests and diseases that can have a big impact on a specific species of tree. Now, fires burn 3 to 4 million kilometres squared per year, and that releases 1 billion tonnes of carbon. Now, this is increasing with time with climate change, but naturally, that is happening without our impact on it as well. Volcanoes we just mentioned just then, they release less than 1% of the CO2 released by humans, but it was an important natural driver of this. Big mega eruptions on our VEI scale can have a big impact in terms of global climate and so on and so on. Then we come on to the human impacts on this as well. Right, farming, deforestation, urban growth, cement, hydrocarbon extraction, and so on and so on. Take some time to read through that. It's got some good facts in it, some of the good basic facts. You've got lots of notes on this, but obviously we are changing the biosphere with deforestation. Our farming practices are churning up the pedosphere and linked to deforestation, as is urban growth. We chop down areas to build. That links into the hydrocarbon extraction and burning cement manufacture as well. So all of those elements are combined by our sort of daily actions for this. So what does this mean then for the carbon budget? Now, the carbon budget is basically how much carbon we've got left until we would cause a 2 degrees C increase in temperature change. That's the magic number. And we've used a certain amount already, and we've only got a certain amount to go. So 1.5 is ideal in terms of how much we aim to change maximum, but we think it's more likely we can limit that to 2 degrees. Now, in 2019, fossil CO2 emissions were growing, but less quickly than they had previously. So that was positive. But we needed it to be like zero or net zero in terms of not having that impact. It's natural gas and oil. That's the main sort of factor for that. And there's some good graphs that you can zoom in on to sort of look at that in more detail. The effect on climate change and the diffusion with the oceans and so on and so on is summarised at the bottom. Now then, last year, we can bring in COVID to this. It caused a record decrease in CO2 emissions, lack of aviation flights, and so on and so on. So this is where the big dip sort of came from. You can see this over from January to this sort of January just now. You can see how that decreased over that first lockdown because of industries being shut down and so on and so on. Lockdown 3.0, which I'm currently in, making this now, hasn't had as significant an impact, but it has still decreased on pre-coronavirus levels. And again, there's some good facts and figures at the bottom there that you can pick out in your own time. So we do need to be careful. But that's all right at the moment. In terms of COVID, it has been positive. We just need to now build on that. Let's be positive about it. Let's think about how we can keep this carbon budget reduced from what it was before. So now we come on to impacts of a changing carbon budget. It's just there, the last little 3, but there's more detail on it here, okay? So how does a changing carbon budget impact the land? If we kept going as we were back in 2019, for example, if we go back to that, what's the impact that's going to have? So, could be good, could be bad. On our terrestrial environment, that means the land, okay, carbon might mean that more plants grow. But it could also mean warmer temperatures puts like water levels under stress, and that might lead to not so many plants growing. So it depends on the part of the world that you're in. At the moment, it looks like it's a net loss of plants with this, but we're still too early to know for sure. That does link to the water cycle as well. High temperatures bake the soil dry. That means carbon basically is lost from that soil, so might increase the amount of pedosphere to atmosphere movement that we've got going on. The permafrost, permanently frozen soil, is thawing. We know that already. That carbon has been stored for thousands of years and might now be released. That might be methane, which is worse than carbon dioxide. We're not sure yet. And the feedback loops in association with this, we're just not sure, okay? But we do have a diagram here that gives you a specific example of the cattail plants and how that sort of has an impact on them and their environment. So that gives you a specific example for this. So that's the impact on the land. Then we've got the impact on the ocean. We've got our key facts. It's going to acidify the ocean. It's going to reduce the pH, make it more acidic. It's going to warm it. We've got melting sea ice, and that has knock-on effects for the albedo effect. It might then lead to a positive feedback loop and speed that up more. It's going to reduce the salinity as we've got more of our cryosphere melting into the hydrosphere. That's going to reduce the salinity of the oceans. And sea level rise with thermal expansion and where land ice, it's not sea ice, where land ice has melted. Then we've got impacts on the atmosphere. So here's your greenhouse effect, the diagram. You need to know that in detail. Land and oceans absorb a lot of CO2, we know that already, but the atmosphere still has a significant quantity that we need to be careful of understanding. So basically, carbon dioxide, methane, they are greenhouse gases. They trap more of the solar radiation that is trying to escape back into the atmosphere. So it's absorbed, and then the long wave radiation meant to pass back to the atmosphere, but the more greenhouse gases there are, the more that it traps, and that's why it leads to this warming. So it is going to warm our atmosphere as a consequence of this. So that's the impact on that there, okay? It summarises that for you. What can we do about this? Okay, well, there's a whole range of things that we can do. We can try to make some international climate change agreements. So this summarises some of the key ones for you. The United Nations is key for this. They host Earth summits and they have a framework on climate change. And basically they have parties, but not quite the fun party. They invite everyone every few years to have one of these meetings and set targets. 197 countries are part of this convention, and they tend to be aiming to reduce harmful human interference with our carbon cycle and our climate system as a result of that. So, key ones for you to know. Kyoto Protocol was 1995. There was a legally binding agreement, that was the first one, to reduce targets. There was different stages to that, and from that the Paris Agreement was the main one. They reached a landmark agreement to intensify their actions to basically speed up their commitment to reducing their emissions. And that was a really important one because it aimed to keep our temperature rise to 1.5, maximum 2 degrees C above pre-industrial levels, what we were back in 1850. And they signed this agreement, but then the US pulled out with Trump because he doesn't like it. So Obama signed up, Trump pulled out, then Biden is promising to, well, it's already promised to rejoin as soon as he gets into power. So that was a really important one because without the US, we couldn't keep the world's warming to 2 degrees based on the promises that other countries had made. They're such a big contributor of greenhouse gases that we needed them to be on board to have the impact because climate change is an international issue. So let's skip ahead there to climate change mitigation a little bit more. Here's a nice little diagram from the textbook that shows you all the different areas we need to think about and how we can, like, very quickly, it's a nice summary there for you to learn some of the basics. But there's loads of stuff we can do. Some of the key ones then, carbon capture and sequestration. This is a technology on the inside of chimneys and stuff, but you can have this technology anywhere, pillows, for example, that traps carbon dioxide using a chemical, literally like it traps it, and then you kind of like put that under pressure and it turns the carbon dioxide into a liquid format, where then you can put it back down into suitable rock strata, rock layers. For example, where we've taken oil or natural gas out of like the rocks underneath the North Sea, that's perfect geology for this to then be squeezed back into that space and locked away for millennia. So it's capturing it, and that can be done before it's burnt, after it's burnt, or oxy-fuel combustion in the burning process. It's then transported and then it's stored securely. So that's the first one. There's actually loads of jobs in this area. In Teesside, we're a hub for that. Next thing was improved aviation practices, more fuel, less flights, less short haul flights, all that sort of thing. That tells you in more detail how that happens, how we can go about doing that. There's 3 different areas in terms of their design and how we can go about doing this in more detail. What else can we do then? Well, we can change our rural land use, agriculture, even people moving around between fields. All these strategies can be used for grasslands, for our crops, for forested areas as well. Reforest them, protect them, have trees in crop areas as well. That helps with water and everything else. All sorts of strategies for you there. Oh, by the way, SOC, soil organic carbon, soil organic matter. That's what those mean as you're reading through that yourself. What else have we got? I think that's the main 3 there. So that's the main ones for you. So then we come on to, how does water and carbon affect climate? How are water and carbon interlinked? So it's all to do with the atmosphere, how that's warming temperatures, how that affects precipitation, the amount of carbon that's held in water, direct link there between the two. CO2 sets temperature more than other greenhouse gases, so that's really, really clear for you. So hopefully that's nice and simple on that slide for you. What are the similarities? How, photosynthesis, they both use plants, how the water cycle is part of that as well, how plants store it, where it's stored underground, got lots of similarities between them. How are they linked between our atmosphere and ocean, and so on and so on. Basically, as the temperatures rise, the ocean expands, evaporation rates increase, that leads more heat to the atmosphere. Warm oceans absorb and hold less CO2, so there's more in the atmosphere. That leads to a change in the cryosphere, more's going to melt, which leads to rising sea levels, all interconnected, and hopefully they're nice and clear there for you too. So then we come on to, how are they interdependent? Or how are they not interdependent? Right. Basically, a number of processes in the water and the carbon cycle need the other. That's what this key thing is. For example, photosynthesis is using the sun's energy, and it needs water to be able to do that. Okay? It cannot happen without that. Transpiration is another one. Decomposition. Important for the carbon cycle, absolutely needs water, that movement of carbon around. The water cycle needs carbon in the form of plants, storage, to move water through it. Carbon is dissolved in water. It's part of that oceanic pump that we've mentioned already. Weathering moves carbon from the lithosphere back to potentially the atmosphere. It needs water to do that. So they are completely interdependent. One needs the other an awful lot of the time. However, it is a little bit biased. You might have picked that up from what I was just saying there. The carbon cycle, no part of the carbon cycle copes without water, without the water cycle. However, some parts of the water cycle do not need carbon at all. So for example, percolation. You might argue the type of rock has an impact, but that's a gravitational force that's driving that process. To an extent, infiltration is as well, although the soil structure plays a part on that, and that is directly related to the carbon cycle. But evaporation, that's using the sun's energy. It's not using carbon necessarily, it's driven by the sun's energy. So it's a bit of a biased way of looking at that one. Biased relationship. They're very interdependent, but not 100% in both directions. So that leads us on to our last part of this, which is about our case study. Now that will be done in a separate video very quickly for you now.